All right, so now what we're going to do is what we just did, but fast. Okay? And in particular, we want to do it in real time. Millisecond level queries. Okay? Now, this is not so simple for two reasons. First of all, we need a real-time view. Whatever we mean by real-time, we need to get the data out of the network that fast about what the state is. And second, we have to actually verify quickly, obviously. Okay? So the architecture, this is what the picture we saw before. And if you squint at this, it actually looks a little SDN-like, right? We're getting data to a central point that's doing something, talking to each switch. Okay, so, and we're getting data from the data plane, same level of abstraction. So what we did in this work, VeriFlow, with a capital F, that's a research paper, with a lowercase f is the company. So just to be clear. You have a huge difference. So you have an SDN controller, and we're going to just slip a verifier underneath there. You could also put it off to the side with an API, but you can do it transparently so you can actually verify the rules as they're sent by the SDN controller. Okay? So this is why you want to do it in real time. Every time the controller makes a change, now you want to verify that change before it goes into the network. Okay? Changes are happening faster in an SDN context. In the human-managed context, changes happen more slowly. Yes, there's some programmatic changes like for route advertisements that come in, but broadly speaking, the bigger changes are humans adding a VLAN or changing some route setting or something like that. But now things are happening very quickly. We need to keep up. Okay? So how do we keep up? First of all, the way we solve that first problem of getting the actual updates is by talking to the controller, right? So conveniently, we have this logically centralized controller that is issuing updates to the switches. So there's an API. There's an API that gives just the changes rather than having to do like a full snapshot of the whole network, right? So that's why getting the data is more efficient. Now, how do we verify it? So VeriFlow, forget everything you learned about the SAT solver, okay? We're going to just start from scratch. Custom algorithms. The first thing we do when we get these updates is we generate equivalence classes. So think about the little diagram of taking a field and splitting it. That's what we're going to do here. We're going to get the rule updates, and we're going to figure out, okay, these rules can affect packets. How can they affect it? They can't affect them arbitrarily. They're going to split the packets into groups. And we want to figure out sets of packets that will have the same behavior throughout the network because they'll hit the same rules. So that's what we mean by an equivalence class. So if we have, for example, these IP forwarding rules, we have these 4 equivalence classes. Or if you're paying attention, actually we could get away with 3 classes where one of them is non-contiguous. Okay? So at a particular device, you're going to have these equivalence classes. Now you need to be able to figure out how maybe remote forwarding rules could affect those packets as well, because it needs to be network-wide equivalent. Okay? Now, when we get a change to the network, we can't start verifying from scratch. We're going to do incremental verification. So what that means is we don't need to look at all equivalence classes in the network. We'll maintain a try data structure, which is basically a way to look up matching rules that overlap with the change. We'll find the things that overlap with the change, and those are the equivalence classes that are affected by the change. Okay? Once we've done that, for that slice of the network that changes, we build what we call forwarding graphs. Okay, so a forwarding graph, this is now a graph data structure representation of what can happen in the network. And this is the model of the network. So you can think of a forwarding graph like this. Imagine we have these 4 physical devices. they may be sliced in that there's different equivalence classes across one device. So this equivalence class, you might travel like this. This one, maybe you end up in a sink here. Okay? So what this represents a little more precisely is a node here is a equivalence class of packets at a certain location. That equivalence class will have a certain behavior represented by the outgoing edges. Okay? But now you can think about all possible behavior in the network as just a directed graph. And by the way, this can also be extended to represent transformations to packets, which would then be a link that is sort of jumping between the planes, if you will. Okay? So if you're modifying some property in the packet, it's still just a link between nodes, but now it's nodes that represent different packet sets at one hop versus another. The point is you boil it down to this graph, and at this point, you have all the information you need to answer queries. This is a model of all possible data flow behavior in the network. Okay? And a query that you write is going to be some graph traversal algorithm. But once you've gotten to this point, it's pretty quickly, it's pretty fast to traverse, to test reachability or whatever you want to, and it's a data structure that everyone is familiar with, of course, so you can write interesting, fast algorithms over it. So you run queries, and in the case of using VeriFlow inserted in the SDN context, you would run those queries and generate either good rules or say, no, that rule violated some property of interest, like it's going to allow data to leak out to the outside world that should be secure, for example, or it's going to disconnect the controller from communicating with the switches. There's all sorts of bad things you could do that you wouldn't want to happen. And then you could actually block the rule from ever entering the network at that point. Right? So the network would never get into a bad state. Of course, you could also use all of this design in a traditional network rather than an OpenFlow network. But then in a traditional network, you wouldn't be getting these incremental updates. Any questions about that? So let's talk about this, how you express properties. What we did was actually say, okay, we're not going to worry about a language to express the properties. It's going to be APIs. So this is providing an API access to a graph model of the network. And if you care about some property, you have to write a graph traversal algorithm that computes it. So what can you compute here? Is it only reachability? It's more than reachability, right? You can check really anything to do with the data plane state. So path length, differences or inconsistencies in paths between one device and another, reachability, loops, of course. All of these are standard algorithms that you can build as library functions. Okay, so to evaluate VeriFlow, we simulated a similar network, although this was now injected with real-world routing table updates taken from live internet measurements from route views. And we were checking for loops and black holes in this case as the properties. And I'll just show one evaluation graph. This is a CDF, and you want to look at the total verification time as the rightmost line there in the CDF. It is log scale. So you can read this and say that 98% of the time, 97.8 updates were verified within 1 millisecond. Because typically, there's only a small amount of the network that's changing. Okay? Sometimes there's a large number of changes, then it took longer. And another thing to note there is that the utility of building this graph, once you've built the graph, the query time is this line here, and it's actually pretty fast. So the pre-computation helps, basically.
So it seems like you are reducing the problem size by this equivalency, and that these groups are based on packets, not on topology. So you are not creating equivalency classes by topology. So eventually you may have some forwarding that by a single change will touch all your equivalence classes.
That's possible. Yeah.
So
Yeah, it
then
could
that
change.
You don't get any reduction. That's probably the tail of your
That's right,
log.
yeah. So you could change forwarding rules that affect every behavior in the network. Yeah, it's possible.
So this is just about destination-based forwarding, right? Longest prefix match.
It can be more than longest prefix match. Yeah.
Am I allowed to change any packet fields dynamically?
Yeah. Yeah. Mm-hmm.
So say I increment the IP address by 1, what does it do?
I'm talking about the published version of VeriFlow now, did not handle packet modifications. And in general, I don't know of a verification system that's handling that kind of packet modification, like increment. And you are, okay, yes. Oh, is this your paper from
I'm giving it up tomorrow.
tomorrow? Okay, yeah. All right.
It's a reason to come.
Excellent. Okay, so we're going to hear about that, and I think that's, you have some work from several years ago as well on stateful modeling. Yeah. So, okay. So this system did not handle that. Okay. All right. Now, I think in the interest of time, one thing, let me just put this out there as a question. I'm not going to end up talking about it, but we were discussing a little. Even in an SDN setting, where you're getting information quickly, you still don't know the exact time at which the network, some change to the network takes effect, right? It's still a distributed system. Yes, you have a centralized controller, but it is a distributed system. When some data plane modification is issued, you don't know exactly when it took effect. And so you never actually have an exact snapshot of the network. So one thing you can reason about is how can we incorporate that timing uncertainty into the model itself. But I think given time constraints, I'm going to skip that. We could potentially come back to it at the end, but I think I'm going to skip for now. Okay, so moving onward, we talked about data plane verification. Now let's go back to the configuration. So now the input to this verifier is going to be the human written configuration. Okay? And these slides, I'm talking specifically about one particular project in this space, which is a project called Batfish that was published in NSDI a couple years ago. And the slides in this section are thanks to the authors of that paper. So now what we have to do when we're talking about the configuration, again, ultimately we care about data flow. The data flow is determined by the data plane, but we only have the configuration as input. So we have to take the configuration and say that is going to result in the following data plane, and then we need to plug that into a data plane verifier, like what we just already saw. Okay? That's how this is going to work. So the challenge here, the first challenge at least, is we need to accurately translate configs to the resulting data plane. Okay? A second goal here is that we want to be able to kind of backtrace and say why something happened. Yes, you found the problem in the data plane. What in the configuration caused that? Okay? And now there's the opportunity to do that there wasn't before, because we're going to be understanding the configuration. So the general approach that Batfish took, which is these authors up here, was to build a declarative model of the data plane. Okay? And this declarative model generates facts that represent the data plane, and then we're going to plug that into a data plane verifier. So let's walk through. Okay. So there's 4 stages here. We're going to generate the representation of the control plane, or the kind of the starting point, what the configurations say. Then we're going to kind of simulate the control plane, its dynamic operation, the routing protocols, and so on, to generate the data plane. That's the data plane generator. Then that basically plugs into a data plane verifier, like what we just saw, but Batfish used a different one that was called network optimized data log, so a safety analyzer, and then the provenance tracker does this backtrace. Okay, so let's walk through some examples here. We start with the configuration. Okay, that's shown up here. So this is your OSPF configuration and so on. We translate this into a representation, a declarative representation. So the declarative representation is a bunch of facts. And then we'll see how we use those facts later. But the example facts are, okay, there's this OSPF configuration. This node on this interface has this cost. It's set with that cost. This node has these neighbors out those interfaces, the physical topology. Okay, so we have this big bag of facts. And then we plug those into the second stage. So the second stage is going to have rules of how those facts generate other facts. Okay? So examples here. Throughout the routing protocol process, we might generate a fact saying, okay, this route was exported by OSPF. This route was installed in the routing table. And then finally, a best route was selected and actually installed in the forwarding plane. Right? Obviously, there's going to be many of each of these particular facts as you dynamically run the protocol. Okay? So this stage basically has a simulator for the routing protocol written in declarative form about how some facts generate other facts. Right? If you have these routes available, then you're going to do this.
So you have a formal definition for OSPF?
That's right. Yeah.
It's a good idea to publish.
So they wrote this. You can download it on GitHub.
I mean, it should be an extension to the standard. If it's a formal definition.
It's not a formal definition. It's a model they wrote in Datalog because...
No, that's not a formal definition.
Well, it's not a formal definition. It's really a model written in Datalog.
Right.
And I wrote it in Datalog because they have a verifier that takes Datalog directly.
Okay.
So basically what it is just a model that you can't really parse as a human, that you hope is correct for million lines of code of OSPF.
Right.
Yeah, of course.
So that's what it is in practice.
So it's formal in the sense that it's mathematically precise, but
Okay.
it's not like it's standardized, I think is what you're saying.
Or
Is that right?
equivalent to the code in any...
Or equivalent to the
in
code.
any
Right.
way.
Yeah, it's not necessarily equivalent to the code. Right.
Yeah. But that's the strength of it. I mean, it would be nice if you had a formal definition in some language with any one of these protocols that you could publish, because suddenly you can verify your code. Because today you cannot verify your code.
That's correct, but the thing is, I think that's an impossible task because it's not only a formal, model of OSPF and BGP. It also tries to understand what the effect of a configuration changes on the BGP code. So it's a formal model of the BGP code, not the BGP spec, right? So it's even worse. So it's much more complicated than that, right?
Okay, thanks.
That's right. So what behind the scenes this system Batfish does is it has basically a intermediate representation that simulates routing protocols. And for different vendors, they have different translators that take the vendor's peculiarities and encode them into this intermediate representation at some level of detail, right? And it's not necessarily an exact translation of every corner case. So it's a model, but we'll come to accuracy. So, okay, so we computed the data plane. Now we're going to plug it into a data plane verifier that will analyze the data plane or may analyze properties that span multiple models for different data planes and compare them. Okay, so an example of that is multipath consistency is one of the properties that would be for a single data plane snapshot. This property they tested saying that, all right, if you ever have multipath, a flow could take this path or that path, like for ECMP. The behavior along those two paths should be the same. It shouldn't be that one path drops the traffic and the other one delivers it. Okay? So when that happens, then we can ask the data plane verifier, okay, give me an example of that path. And then you could also, in this stage 4 of reporting provenance, trace back, okay, these facts happened. What caused those facts to happen, right? That path is there. Why is that there? That got installed by OSPF, which got, that route announcement because ... back to the facts that you started with in the configuration. So that traceability happens automatically in this declarative language. So that's an advantage of choosing that declarative language to model the control plane and the data plane rather than, say, just using VeriFlow to try to plug into here. Okay, so also in this paper, the properties they tested were some interesting ideas. I just told you about this multipath consistency property. You want to know if packets could travel multiple paths and different things end up happening to them. Failure consistency is basically saying you can take down a link and you're still reachable to destinations. Destination consistency, this is maybe a little bit less obvious. Which is that you're saying if you're an ISP or a network in general with multiple customers, there should be at most one customer per delegated address. So in particular, a way to test that is if you failed the link going to a certain customer, that address should no longer be reachable. And if it is, then you have maybe some conflict. Okay? So... okay. So the implementation supports several different vendors, a number of different features of those vendors. So this was a lot of work because of what we just discussed to at least model even the basics of the differences and compiles down to this intermediate representation. They evaluated on 2 university networks with 21 and 17 routers respectively with somewhat different designs. I'm not going to go into that too much, but found a number of violations of the various properties. And I'll point out just a few things here. The numbers are the number of actual violations, and then in parentheses is the number of groups of violations. A group is all caused by the same root cause, right? So there are many different flows that may be affected by one particular problem. So this is in parentheses the number of problems. So there were many violations. Some were confirmed by operators as actually being real problems, and some were fixed. The differences here are in the failure constraints, like 7 dropping down to only 2 of those were confirmed as problems. The reason being, in places, the network was intentionally not resilient to any possible failure, okay, due to basically cost reasons. Okay, so those invariants are finding actual problems, again, kind of further confirming that there are real issues out there. At least when I started working in this area, I had no idea what we would find, right? I wasn't coming at this from a network engineering background, in fact. So I didn't know when we looked at our first network, okay, is there going to be anything interesting there at all? Or maybe, yeah, theoretically there can be problems, but it doesn't happen in practice. So this is some more confirmation that there are issues you can catch in practice.
Failures is the most inaccurate measurement, both networks. Why is that?
Yeah. So that's a good question because it's a question of false positives, basically. You found some problems. Are they real problems? And in a sense, there's no false positives. At least the issues here are not false positives because you expressed an invariant and the system was telling you, hey, that failed, and it really did fail. Okay? Now the thing was that invariant wasn't matching with the network operator's actual intent. The network operator's actual intent was, I'm going to take my chances on this link because I don't have enough money to build a whole second redundant connectivity to this remote site. So in practice, you'd probably want to apply that particular invariant kind of scoped down to some part of the network where you do expect it to be resilient. Now, there could be other kinds of false positives as well, like if the model is inaccurate in some way, but that's not happening here at least. Okay. There's some performance numbers depending on the size of the network. We're talking basically hundreds of minutes. I'll just mention the hardest thing here is failure consistency because there's 199 links you could fail, and each of those you're going to build a new model in the worst case at least. You could think about how to accelerate that. But something they pointed out in the paper is these can be fully parallelized across all of the failures that you test. So if you're willing to spend some money and spin this up on, Amazon, then you can do that. All right, so let's compare advantages and disadvantages of approaches just to wrap this section up. And we kind of touched on this already. If you're analyzing configurations, the big advantage is this enables what-if analysis. What if this link fails? What if I add a device over here? What if I change the OSPF weight on this interface? Okay? And then I can compute the data plane that would occur, or at least to some level of accuracy I can. Second advantage is being able to trace back to the configuration cause of some data plane effect. Data plane verification. First of all, it's useful as a component in configuration analysis, but also you get that accuracy, right? So now, you'll see all of the effects of all of the corner cases and bugs and issues that would have been very difficult or maybe even impossible to really model at the configuration level. Okay, so that's kind of the basic trade-off between those two approaches. Okay, so what I'd like to do with the remaining time is two things. First, we dove deep into a couple areas. I want to step back and look at kind of the landscape of papers across this area and some of the history and some of where the research is going. And then I want to save time to talk a little bit about verification in the real world, in real deployments. So all research stands on the shoulders of some earlier techniques. And we kind of started here, but there was work before this. And I don't have time to talk about all of these in detail, but I'll point out this paper by Jeffrey Shia and co-authors listed there that was, in retrospect, basically an early form of data plane verification. What they were specifically doing was taking an IP network and computing reachability sets at the level of designing an algorithm for that. And flow checker was also an early work. This was in a SDN context. The contribution here was, as I mentioned, arguing for, in a quantitative way, the architecture of data plane verification and building that system and running it in real design. Just after that, header space analysis is another data plane verification system that uses a pretty different algorithm that's based around representing packet header sets as a difference of cubes representation. And I won't go into that in detail, but what they do is reason about as you kind of inject a virtual packet at a starting point in the network, that virtual packet representing a whole set of packets gets kind of narrowed down to more specific behaviors as you go through the network, and you can explore each of those behaviors. So that's what they call header space analysis. For time reasons, I'm not going to go through all of these, but NetPlumber is a real-time version of header space analysis, and CCG is our paper that deals with verification with awareness of temporal inaccuracy. Okay, now there's a group of papers that are optimizing for performance in various ways, including parallelizing verification. If you're in very large networks, for example, let's say a Google data center, you don't want to run on a single machine. Atomic predicates and DDNF both deal with how you represent a set of packets. Okay, and that's different actually in these different designs. Whether you're kind of implicitly doing that with constraints, like in a SAT solver, you're describing sets of packets by the constraints. In VeriFlow, we were describing sets of packets using ranges in this trie data structure. In HSA, there's this difference of cubes. And then these are alternate designs for how you deal with those sets of packets. So that's kind of an algorithmic acceleration you can look at there. Okay, configuration verification. Again, we started here, but there was work before that as well. And I'll just mention the earliest that I know of, which was Nick Feemster and Holly Balakrishnan's work on analyzing BGP. And this was configuration faults in BGP with static analysis. So very forward-looking paper, important paper. The difference between this work and what came later was making it effectively what I would call general purpose, right? So RCC deals with specific properties in BGP, whereas Batfish, as we saw, builds a full network model of everything that can happen in the data plane, right? And then that's general. It shows you what happens in terms of actual data flow, and you can do interesting things with that. Bagpipe is interesting because it's going beyond Batfish to reason about more sets of things that could happen. What do I mean by that? Batfish started with not only a configuration, but also a network scenario. For example, the routes that are being injected into you by your neighbors. Okay? So now we can abstract over those and say, for that environmental differences, is there anything, if that's uncertain, could I get into trouble with different route announcements or something like that? So that's what Bagpipe looks at. Okay. Now we can start looking at richer verification models. Okay? And already I missed a paper that I should have put on here, which is Kosin's paper from, I think, 2013.
The conference version is last year, so it's
okay,
that one
it's
is
more recent.
obsolete.
Didn't you had a early, that was a workshop version?
Yeah.
You were thinking about these ideas earlier, so I should have that on here. I'll add it after if we share the slides. But those works deal with mutable data paths. So that's an additional complexity in the network model, whereas what I discussed with Anteater and VeriFlow doesn't deal with that. And are you going to tell us more about that tomorrow?
Yeah, so I guess what Brighten means by richer data plane is more like what do you do when you have a data plane that's programmable more than just match action, right? It's just like, and the action is forward. So the action could be change a header field or, save some state or something. So all of the others, all the previous work does not really cover that part of
Right.
these work.
So changing header fields in flight is covered by some of those earlier works, but not changing state at the
There's a
switch, and
big
maybe
dis-
not even in the range of ways that you have in mind.
Specificity. So, for
Yeah.
instance, like header space, which is sort of
Right.
the simplest to understand.
Yeah.
Basically, what it says is, if you give me a header, I will model the box by telling you as a mathematical function, right? So this is the input and this is the output.
Yep.
Okay, and the header can be concrete, 0, 1, and I will output concrete, or it can be don't care, right? Which
Mhm.
means can be any value. And then the output is don't care also, but there is no relationship between the input don't care and the output don't care, right? Do you see my point? So if I wanted to
Right.
say something like decrement the DTL in
Mhm.
header space, I would have to actually specify if the DTL is 255, then it's going to become 254. If it's so, it's like the lack of expressivity is really affecting these things. So it's not. I mean, they are simple, but that's why I'm saying that they don't really work for mutable data planes because. To program in those, you'd have to come up with huge transfer functions that wouldn't really work, right? So,
Yep.
and that's an example for a header space, but I'm sure NT is similar, right? So,
I think so.
yeah.
Yeah.
So that's
Mhm.
that's the
Okay, and you're going to talk about that tomorrow. So
yeah.
we will we'll learn more about that. This one I'll mention a little bit because this is pretty interesting. Again, the level of abstraction. Everything we did assumed that here's the data plane, and then the hardware is going to execute. You got the tables, it's going to do its thing. Okay? Well, what is the router actually doing with those tables? How does it actually compute? When a packet goes into the box, it does some stuff. And it especially does some stuff as we're moving to software packet processing devices that can do more complex computations in the fast path. So this paper, which got a Best Paper Award actually at NSDI that year, verifies the actual code of the packet processing fast path.
It doesn't really work.
How would you put it?
So So basically they say, look, we can symbolically execute real C code, and that's the real data plane. In practice, what they do is they take some click elements, they rewrite them manually to make them friendly for symbolic execution, and they verify those with
Yes.
some caveats.
Yes. Yes.
So
yes.
what they end up verifying is also a model of the data plane, not the real data plane, except that the model is also written in C, which is probably the wrong language for modeling. If you want to model, you might as well use something else, right?
Yeah.
So it's
Yes, that's true. Yeah. So I guess one way you could put that is if you're willing to constrain how you write the data plane,
actually no.
then it becomes verifiable up to a certain level.
No, you can't, because there's a fundamental trade-off. So the fundamental trade-off is the following. Generally, things that you can symbolically execute run really slowly, and the opposite, right? So intuitively, for something to run fast, you have to have a huge branching factor and very few cycles spent per packet, right? Think of a hash map, okay? So I will do a lookup, and then the lookup tells me what I need to do with these packets, and I'll just do like three instructions, and I'm done, okay? Now, if you symbolically execute a hash map, it just goes crazy, right? It's just
Yep.
the whole
Yep.
thing just
Yep.
goes to,
Yes.
right?
Yep.
So basically, what you will end up doing is if you really want to verify, let's say, this box that has a hash map in it, you will basically model it based on the number of output ports it has. Okay, so basically it's like the equivalence classes you were talking, except now the equivalence class is stuff that comes out on the same output port. And you'll try to basically group together all those branches that are going out on one port, one output port, and make sure there's a single branch, not like 100,000 of them, right? So, and because of this, because you're now grouping together, it's as if when you do a Mac, like a switch, it's as if you wrote the following code. When the packet comes in, duplicate the packet, send it to all output ports, and then on the output port you say if the Mac is this or this or this or this. So you have like a linear, Boolean formula that you have to verify. That's basically linear number of MAC addresses in terms of complexity. If you had a hash table, you'd be like, okay, what's the destination MAC? I will just do a single lookup in all of one and just keep going. So basically, these two models are, one of them is good for runtime, the other one is good for verification, and they both suck at the other task, right? So it's actually not possible, especially from a symbolic execution point of view, to write. This is sort of well known in software verification. There's a fundamental tension between runtime and verification, like being fast at runtime, being fast at verification. And of course, with a data plane, you want it to be fast, you can't have it to be slow. So therefore, the Argyrakis paper is the biggest hoax in, and it got the best paper, so there you go.
Okay.
I think when we upload this talk to YouTube, we can have the authors respond in the.
I've spoken to them.
Okay.
they know my opinion.
All right. We will leave that there. So.
So it's not
Okay, so another group of directions which I think is pretty interesting as we're moving to more programmable networks is to write your controller, the control software, so that it itself is verifiable. Now that can be assisted in some cases if the language itself helps, right? So in this new world of SDN, we can envision that we have a new programming language and we're going to write our network software in that language that can perhaps help, right? So that's what a couple of these papers are doing. So that kind of gives some overview of some of the directions that this verification work is going. It's certainly quite active now, and you can find a lot of papers, and you'll be hearing about some of the more recent ones tomorrow. Okay, so any questions before the last section of the talk?
So regarding the last research direction.
Yeah.
So is there hope that people will actually transition to any different languages just for the purpose of verification being easier?
Will people transition to different languages? I am a bit skeptical, I think. I think certainly for network operators, I would think the answer is no. But, possibly for vendors that are producing solutions for those operators. That's a different question, right? You will often see SDN papers written to say, oh, now the network operator can program anything they want. Not going to happen. It's not going to happen. They don't want to be programming, right? Generally speaking, they have some high-level goal that they want to achieve, and they want the software system to do it for them, basically, right? So my guess would be no for network operators. For whoever implements the SDN applications, which is generally not the operators, then there's a bit of hope because that's critical software, right? And there is critical software that people do put effort into verifying, like software for the space shuttle, or so that's the one reason that there might be hope, I think. But any opinions from the audience on that?
So I didn't read the papers, so I have no clue how these software languages look like, but if you compare it to formal model checking in VLSI, then writing formal models or programs that are easy to do formal proof on, then you go back to Sugar or CTL or stuff that nobody can read. So that's my intuition of that. So
to add to that, I would say that I think the control plane is so complex that there's no real hope of ever verifying it or even modeling it. So that's why I think that Batfish and all the other configuration verification tools, despite some of the success they've had, I think they're dead end in a sense because the code is so complex. I mean, this is a really large civil system with it's probably undecidable to tell whether it's correct or not, right? So I think the only hope is data plane verification. The hope is to do it fast enough and to do it automatically, like to be able to generate a data plane that is somehow provably correct without the operator, just taking the output of the control plane and just instantiating it. I think that's the way to do it. I think what Brighten showed was that if you have these very simple data planes, where you basically, it's obvious that they are correct because you've extracted the rules from the forwarding table. It's clear what the router does is probably fine because it was verified and used for like ages. So there is no gap from what you're verifying, assuming you got your code right, to the actual network. I think that the trick part is that because the networks are becoming much more programmable with middle boxes, NFV and P4 and all this stuff, it's not really just longest prefix match, it's really a program. And now the thing is, you could try and directly verify the program, which is like something like P4, but the thing is there will always be different data planes. So you will have a P4 data plane, you'll have a C data plane, you'll have an OVS data plane, you have multiple data planes. So the question is, first of all, what's the right language to model all of these data planes and verify them? And then how do you go from this language to something that is equivalent? Right? Because if you could do this transition from the data plane language to something that's equivalent, then the problem is more or less solved, right? With the caveat that if the control plane has some problems that are not affecting the data plane, then you're still, it's not a fully complete solution, right? So there's still some work to be done there, but I think it gets us most of the way without needing any operator involvement. The minute you say the operator has to formally verify or formally do anything, then you're gone, right? So there was a paper, you didn't mention it, Brighten, there was a paper in NSA this year that basically shows how you can, so it's like a theorem prover approach to network correctness, starting from the specification, going all the way down to the OpenFlow tables. And it's what they have is basically a language and a tool that helps you to refine more easily, but it's still, it requires expert,
to be in the loop to
a lot, expert in the loop to be able to like help the prover, with every refinement step. So that is obviously, of course, you would write the paper because it's interesting. You apply normal formal verification techniques directly to networking, but that's a real dead end. Nobody will ever do that unless it's the network inside an airplane or something. If the network runs in an airplane, they probably did it already, so we shouldn't bother.
Hope so. Okay, let me wrap up in the next few minutes, and then we can have time for more questions. All right, so let's look at how this is playing out in the real world, because there's actually a lot going on now, including 3 startups that I know of pursuing general purpose, what I would call general purpose network verification meaning for your average enterprise and all of the complexity that they have in it. One of them, of course, being VeriFlow, but another being based on Batfish. So maybe they will test out your prediction of whether there's any hope in configuration verification. There are also what I describe as more special purpose efforts that at least 3 of the hyperscale cloud companies are pursuing. And at least 1 major network device manufacturer. So there's a lot just within the last year or 2 that's spinning up right now. So it's going to be very interesting. And this has come to the attention of Gartner, which is, if you're not familiar with them, it's a research analyst firm that works with major enterprises to advise them on technology. And they're grouping verification with a new area that they call intent-based networking. And that word intent has been used by others as well. So intent-based networking, meaning the network is driven by the end-to-end goal. Okay? And that can sound a little bit like SDN, but it's not necessarily SDN, right? SDN systems might be lower level, but often they do involve intent. But you can have an intent-based system that's maybe not SDN as well, right? It's just this idea of describing the end-to-end business objective, like, this critical service needs to be reachable to each of these customers, right? Rather than focusing on the detailed implementation. So, of course, verification is part of that because the intent is what you verify.
And Brighten?
Yeah.
All of these focus on data plane verification?
Not all. IntentionNet is a startup that is apparently based on Batfish, which is configuration verification.
That's a tool.
That's right.
So they don't use data plane verification? I mean, Batfish does use data plane verification. It says that.
Oh, right, as an internal step.
Yeah.
Yeah. So if in that sense, yes, ultimately it's computing a data plane. And of course, I have no special knowledge of what they're doing internally. You can go to their website and look. Okay, so with all this going on, what have we learned? I wanted to describe in the last few minutes kind of 5 takeaways that going through this process. I've learned some things that I expected, some things that were a little bit unexpected. Okay, so number 1, this is actually useful. It's actually a real need out there because networks are quite complex. You do have many different technologies, many different providers, many different cloud providers. And actually, in many cases, these new technologies like SDN, like cloud, that are intended to help automate, and they do help automate, but automating is not quite the same as making something simpler. Now there's another system in the mix. It's not, if you deploy an SDN solution, it's not like you're wiping away your whole network and starting from scratch with this simpler system. You still have everything you had before, and you have this new thing. You have the SDN overlay, and you have a physical underlay, and you may have multiple clouds and so on, right? So at least for the time being, and this is really something persistently that enterprises always have to deal with, is that there's always continually new technology, but it's hard to change the old things, right? So that's part of where the complexity is coming from. This isn't a snapshot of an actual enterprise network internals. Actually, I can't. Unfortunately, I wish I could show you a diagram, but this will have to suffice. It does have some wireless here, and it has series of tubes and things. Anyway, so it's that level of moving parts. So the need comes from complexity. This was from a survey we did that said, has growth in complexity led to more frequent outages in your network? 59% say yes. And almost everyone, I forget the number, but it was in the 90s, said that yes, there was increased complexity. Second is change. Humans making changes to a complex infrastructure. That's often when the problems arise. They can be very frequent changes. So DISA mentioned, so DISA is the service provider for the Department of Defense. And in a talk, they mentioned that they have 22,000 changes to the network per month. So with this rate of dynamics, of course, things can go wrong. And manual processes, we talked about this a little bit, that yes, it really is manual. And just to illustrate that, something that surprised me coming from outside the network engineering world is that very many enterprises, just for the task of mapping their network topology, draw it by hand in Visio. And that's even at large scale. And of course, they can't draw the whole thing. And the result is like a lot of PDFs that you have to kind of thumb through that are immediately out of date. And it takes a huge amount of time to do that. So, and that's one example of the manual processes. Okay, how is it actually useful in practice? We have observed at least a number of use cases. There's a lot of use cases, right? Because it's verifying. You can verify anything. You can put it in there. But there's 4 use cases that come out pretty commonly across across government, manufacturing, retail, internet media, a lot of different kind of enterprise networks. These uses pop out. One of them is verifying network segmentation. So segmentation means that you're drawing boundaries within your enterprise. The need here being that previously, often enterprises relied on a perimeter security model. You harden the perimeter, once you're inside, it's open. And as probably many of you know, now the situation is you have to expect that the perimeter is going to get breached somehow. Someone brings in a laptop or clicks on a link, or there's a port open, whatever it is. Once there's a compromise inside, you want to limit that damage as much as possible. And as we saw in the previous talk about SDN, SDN is helping with that process with what's called microsegmentation, so that you draw very fine-grained boundaries around applications where you can. But the broader story here is you want to have those layers of protection, so you have defense in depth. You have multiple layers of defense. You're protecting the host. The network is helping in case the host doesn't protect itself. So in a very complex infrastructure, how do you know if you've actually segmented, right? No one is going to tell you that it's not like an outage situation, for example, right? That if there is a vulnerability in the infrastructure, it might just stay there for months, years, until it's exploited. Availability and resilience, also extremely important. And we saw some examples of this that we talked about earlier in the talk, where you might be vulnerable to a failure. You of course want to maintain availability and also resilience even if there's a failure. Compliance involves aspects of security as well as availability, as well as just documenting the network. And then incident response. So sometimes something happens, right? Hopefully you catch the problems, but occasionally there are incidents. When there is an incident, you want to understand the network as quickly as possible. So this means asking questions interactively. Okay, so third thing that I think we've learned, which is that extracting the abstraction is not easy. Okay. We talked about, if you have software verification, you get a program, and given this program, you're going to assume that there's some formal specification of the language, and then you're done. And hopefully the compiler actually, matches that, and the hardware actually executes correctly, and so on. But those are safer assumptions. In the networking world, if you want to extract the data plane state, there is no universal API to actually get the forwarding tables and the other various tables that you need, because there's a lot of them, right? It's not just a forwarding table. There's ACL tables, there's MAC addresses that are used in various ways. There's multiple kinds of ACLs and multiple kinds of forwarding tables for different protocols. So the least common denominator is SSHing into a box and running commands that say, show IP route or whatever, and print that out. And that's not intended as a programmatic interface, but that's the least common denominator in extracting information. Not only that, once you have those tables, there's no formal specification for how that state relates to the functionality of the device. What do I mean by that? If you look inside a switch, it's not just a table. There's a whole pipeline. Packets go in the physical port. There's an ingress port flow table. VLAN stuff happens. ACLs can happen over here. Even this is a simplification. Then you have multiple routing tables. You have more ACLs at the end, and the details of how this happened in a specific hardware device maybe are not exposed. And so that kind of gets to the last point, which is that there can be vendor-specific behaviors for all of this. So it's a lot of work making this accurate. Even though I said that the data plane gets you as close as possible to an accurate view of reality, it's still not trivial. And there is some hope, I'll mention. There are vendor-specific APIs, still vendor-specific, but at least it's an API. And SDN products are moving more towards this model, of course. So the industry has realized that that's the right direction with clearly specified APIs, but it's going to take a long time to get there. OpenConfig is an interesting effort, if you haven't heard about it, to do some standardization as a layer on top of legacy devices for provisioning configs as well as monitoring. But it's a little bit early stage right now. Okay. 4, this is supposed to say 4, not 3. That's a typo. The model verifier separation is actually useful. What do I mean by that? Remember that I mentioned in the VeriFlow architecture, we compute, as described in the paper, a forwarding graph, and then you can query that graph with various questions. And VeriFlow is not the only design that Verifier that has that kind of design where you're not verifying a property per se, you're building a model. And then you can ask the model questions. Okay? And so when I spoke about this a few years ago, I said, okay, looking ahead, there's an opportunity that you can think of this model as kind of a real-time knowledge layer, and then you can have applications on top of it, of which verification is just one. And in fact, that's true. So you can verify, you can also visualize, you can search interactively, you can maybe write your own API-based programs that query the model and so on. So this is something that we found is in fact useful in practice.
You can predict performance. You could add SLA and performance on top of that.
Yeah, you're absolutely right. Yeah, so you could say, all right, I have this hypothetical traffic matrix. Let me figure out what effect it's going to have on the network. So the last, this should be number 5. I'm not cheating you. I promised you 5. Is that we need a shift in thought. So verification is intent-based. It's about the end-to-end goal. And that's different than network engineers typically think today. So network engineers typically, and I'm overgeneralizing, not everyone's the same, but often think about a box. And if you ask them, what was that box supposed to do, you get answers that are like, okay, well, it should have a default route, and SNMP should be configured, and ... right? Should maybe match a template config. Those are low-level properties of a specific box. They're not the end-to-end goal. So we need a shift in thought from the network as individual devices with individual config knobs to the network being one system with an end-to-end intent. And at that point, you're really thinking about the network as you're building a distributed system. And it's of the level of complexity of building your own piece of software, right? So this is a difficult transition that the networking industry is undergoing. Probably there's going to be a pretty big shift in the skills necessary for architecting and operating an enterprise network as well. So I will leave it there, and time, maybe a few minutes for questions, but if there is. Okay, thank you.